So we're going to look today at the idea of doing a three-dimensional drawing, and this is what we're going to call the dash and wedge notation. Dash and wedge Lewis structures. Okay, let's take a look at an example of a molecule that we've done before, which is CH4. And remember, the colors don't matter. I'm just going to use this from the standpoint of a model. So the greens are going to be the hydrogens and the black is going to be the carbon. So our molecule is CH4. And you might recall that the basic Lewis structure for that would be drawn like this. We've got a total of 8 electrons. So we put one pair between each of the pairs of atoms there to make 4 different bonds. And now we've got this CH4 molecule. We'd classify it AB4, and that AB4 then is going to tell us that it is a tetrahedral molecule. However, given that this presently is a two-dimensional structure, it's not going to be very helpful for us to visualize it as it would be in real life in a three-dimensional world. Consequently, we're going to invoke this dash and wedge system. So dashes and wedges. We're going to use a dash, just a dotted line, to represent into the plane. And the plane is the two-dimensional surface on which you're drawing. We're going to use a wedge to represent out of the plane. And that out of the plane, again, refers to that two-dimensional surface on which you are drawing. A regular old line, just a straight line, is going to be in the plane. So looking at the molecule then, as I've drawn it presently, these 4 are all in the plane, which can't happen because a tetrahedral molecule is going to have bond angles of 109.5 degrees, roughly, for CH4 anyway. So that obviously is not what we're dealing with here. These angles are 109.5, they're not 90 degrees. So to get as far apart as possible, which remember is the idea behind VSEPR in the first place, you're going to have to orient them in space to achieve 109.5, which is going to be this tetrahedral molecule. Now, so how do we draw that? Well, it's a matter of choice. So I like to use a piece of paper, and I've got my model that I've created. And I want to try to put, at least for this molecule, 3 things in the plane. So using the piece of paper then, I can show this, that the 2 hydrogen atoms and that 1 carbon atom are in the plane. That is the two-dimensional surface, right? And then if I rotate it a little bit, you can see that one of the hydrogens is going behind and one of the hydrogens is coming out. So 2 H's in the plane with a carbon, 3 atoms in the plane, 1 H going behind the plane and 1 H coming out of the plane. So to draw that, I'll simply make it with a carbon in the plane. You can visualize it now. 2 H's in the plane. Sorry, 2 H's in the plane. There we go. 1, 2, 3 atoms total in the plane. 1 going behind, so that's going to get your dash, and 1 coming out at you. That's going to get the wedge. So it's not real pretty, but at least it can give you some kind of a technique by which you can establish a sort of a virtual experience to have the molecule in 3D. Let's take another example. Let's do PCl5. I think we did like maybe pH5 or something the other day, but regardless, if you follow the rules, you'd say there's 5 electrons for phosphorus and 5 times 7, because chlorine's in group 735, give us a total of 40 electrons. Phosphorus is an exception to the octet rule, so we can have more than 8 around it. So our chlorines then surround the phosphorus. We put in our bonds. That represents 10 electrons. We have 30 left, so we complete the octets of those surrounding atoms. Remember, don't get hasty. Avoid just throwing in double bonds and triple bonds and all that stuff, because you can make mistakes pretty quickly that way. So then your molecule starts to look like this. I'm not going to draw the lone pairs. in this sketch, as we've already seen them. You put your ABE notation onto that, and you come up with a structure that's AB5. And AB5 then is trigonal bipyramidal. Okay, again, a three-dimensional structure. So pyramid is, right, three sides in the structures that we've seen so far, and bi means two, so we should be able to come up with two three-sided, or two pyramids, four-sided pyramids that are adjoined by the center plane. And so this would be PCL5. Okay, trigonal bipyramidal. So you can see the bond angles. We've got 90 degrees here. There's the 180. And so then the 120s on the equatorial chlorines. Okay, so the question then is how we're going to draw that. There are a couple of different ways we can do it. My personal favorite is to try to get as many atoms in the plane as possible. So in this structure, it would be possible to put 4 atoms in the plane. I get my piece of paper and I line it up. So now I can see this atom on my right side here is still in the plane. I just can't put the paper around there. And I've got the other 2 chlorines laying on the paper presently, and then the purple in the middle for the phosphorus. So that's 4 atoms in the plane. So if I was to draw that, P goes in the middle. I have 3 chlorines in the plane. And you can even simulate the 120-degree bond angles if you want to get tricky. Then I've got 1 going behind the plane. Yeah, there's 3 in the plane. Let's get it oriented correctly. There we go. So you can see there's 1 going behind the piece of paper. That's the plane. So the dash showing the chlorine going behind. And then lastly, we've got 1 coming out at us. So I can draw that lots of different places, but there's a wedge there perhaps. And there's my chlorine. Okay, so what's the idea then for today? The idea would be then on your paper, we had the Lewis structure we drew before, and then I said ball stick model, you can try it if you want. So I'd like you to go through these structures and try to do your 3-dimensional drawings using dashes and wedges. Don't worry about molecular polarity yet, we're not quite there. Also on the back, if you start looking down, here's a fun one, N2O4. You may not get that one yet, that's okay. ClO3H, hint, the H is attached to an O, and the O's are attached to the Cl. That will help in terms of how you draw that, okay? So that's the plan for the first part of today.